Good afternoon, everyone. Thanks for joining me after lunch. I hope everyone's been having a great show so far. So just to introduce myself, my name is Maughan. I'm an engineer by background. I'm a fellow of the Institute of Mechanical Engineers. I'm the managing director of a company called Transense Technologies, PLC. I've been with Transense now for about 4 or 5 years. Prior to that, I had a business in the electric vehicle, electric drive system development space. So Transense is a company which we're exhibiting here today. The business was founded in 1991, so actually it's not a new company, which sometimes it feels like a new company, but it's actually been around for a long time. We're a public company. We're listed on the London stock market, on the AIM market, which is like a specialty stock exchange for smaller companies. It actually listed on the stock market in about 1999, so just before the year 2000, when one of my colleagues was actually born. We've got about 30 million pounds that have been invested in developing the technology, over 50 patents, and we're based in the UK, in Oxfordshire. We're still a small company, about 35 people. So up until a few years ago, we had 3 divisions in the business, but one of the business divisions was sold, and we have now 2 business divisions. The Transense business, which I'm going to talk to you about, the key technology, and the Translogic business, which is doing something completely different to do with tire inspection. So the Transense business is really what the company was founded on. We develop and supply unique sensor solutions using SAW technology, which is surface acoustic wave, and I'll explain what that means on later slides. We focus on the aerospace, the automotive, and the medical markets, and particularly robotics. That's a very growing space for us. And we work with some very significant OEMs, and we integrate SAW technology into their products for measuring different properties. So just to set the scene a little bit, thinking about conventional sensors in the test and measurement market. So in terms of measuring things like torque and force, I think probably a lot of people are very familiar with strain gauges and displacement sensors, so twist angle sensors, and magnetostrictive or magnetomechanical sensors. So typically, normal sensors for measuring torque in particular require the use of these flex structures, so something in the component being measured that allows it to have enough displacement or torsion to create a measurable effect. There can be some issues in terms of electromagnetic background and magnetic interference, so it's quite difficult to develop systems, and people who make torque sensors in particular know how hard that is on a day-to-day basis. They don't stay the same, so performance changes over time. Typically, people will be familiar with creep and hysteresis. Dynamic response is a very difficult area for torque sensors. There's no international standard for dynamic torque testing, and we always find it difficult to characterize the dynamic response of a torque sensor system. And then also, it can be very difficult to make these things in high volume with guaranteed repeatability. Lots of conversations on our stand the last day or two about making strain gauge systems, for example, which can be incredibly challenging. So, that's what we're used to today. What we're going to talk about is something that's completely different. So surface acoustic wave technology, which is, as I said, what Transense was founded on, is a very, very unusual sensor technology. So what we can see on the right-hand side of this slide here is a SAW AQP. So that's a surface acoustic wave all-quartz package, and that's about a 40 times magnification. So this is shown in its raw form without a lid. And what you can actually see on there are 3 sensors, which we call interdigital transducers. So we really like an acronym. So SAW AQP IDT is visible on the surface there. And actually, the reason why they're appearing green is because the spacing of those interdigital elements is so close together, it's affecting the light that's reflected off the component. So under a microscope, the SAW elements look like this. So they are little fingers, hence the name, that interlock, and that's what we use for measuring. So on the face of it, that's quite a simple looking part. We manufacture these on piezoelectric material. So sometimes the SAW principle, it's called the reverse piezo effect. So we're feeding an RF electrical signal into this component, and then we're getting a response from it. So always a piezo substrate. We make these on a wafer. The wafer's metallized, and then we use a lithography process to produce this pattern, which is obviously very, very tiny, so you can't see it with the naked eye. This particular sensor is designed for measuring torque, so that's its particular purpose. If I go to the next slide, you'll see why. So, example here for a torque measurement system of how we'd organize the sensing elements on the part. So what we're showing here is a shaft. It's obviously a very basic illustration of a shaft, and our saw sensing element. So with the two sensor IDTs mounted on it. So if you know about the mechanics of shafts under torsion, you know that the principal strain on the shaft due to the torque is at 45 degrees to the axes of the shaft. So it's actually it's a deliberate organization there of our sensing elements on the chiplet. When we place them, they're orientated exactly with the principal strain due to the torque on the shaft. We use two sensing elements on the shaft. So what you can see here is a cross section. So the two parts, they are slightly different. So we call it HF and LF. So the H is high frequency and the LF is low frequency. They're pretty similar in terms of the makeup of the parts. So in total, between the HF and the LF saw, there's actually 5 individual IDTs on each torque measuring system. So we're doing that on each side of the shaft so that we can compensate for bending loads. So not a particular requirement of the sensing system itself, but in order to help us in terms of how we're measuring. So what we're actually doing then on the shaft is very simple. If you understand the saw principles. So we have our sensing element on the shaft, but we have electronics off the shaft. So we feed the saw elements themselves with an RF signal. So our chiplets are designed, or the current ones are designed to work at about 450 megahertz. Now, the key thing is each one of the IDTs that's in the saw system has a unique frequency. So we actually have a band around the 450, so 420 to 450. We're dividing that up into 5 individual bands. So we address each sensing element individually, and we listen for its response individually. So we do that. The response is coming from that backscattered signal, which comes back to our electronics. And that all happens over what we call an RF coupler. So it's quite easy to think of the RF coupler as an antenna, and I'll often describe it as an antenna. If there's any antenna engineers in the room, please don't be offended, because I know it's not actually an antenna. It's a very simple strip component, which is giving us an RF couple between the two sides. So, in principle, that's a fully functional torque measurement system. And I appreciate that doesn't look overly interesting in terms of a line diagram. But to give a better example, so we supply sensor technology into the motorsport industry. And actually, our partner there is a business that used to be called McLaren Applied, which is part of the McLaren group. It's now called Motion Applied. And this is an example of a shaft from IndyCar. So the IndyCar Championship uses our sensors to monitor the torque between the engine and the gearbox. So this is a gearbox input shaft. You can just about see the splines on either end of the shaft. For obvious reasons, they don't like us showing the whole shaft. As a practical example, we have an RF coupler. So this is a different style of RF coupler to the previous slide. So this is what we call a radial coupler. And we have the sensor installation is mounted in this area of the shaft. So there's a key feature of that shaft is you'll notice the diameter of the shaft is swollen slightly. And that's because what we are doing with the saw technology is we're optimizing the strain that the sensor is seeing in that location. So we increase the diameter, so we're getting the strain into exactly the right range. So actually, we're making the shaft stiffer than it was before, which is different to, normally if you're trying to measure torque, you have to make the shaft more bendy than it was before, but we're trying to make it stiffer to put the torque into the range of plus or minus 400 microstrain when measured in that location. The other feature that you'll see there, which maybe you can't see too well from the floor, are these, which we call bullhorns. So they serve a very special purpose, and again, not particularly to do with our sensor system, but on the shaft that we have here, we have some splines, and they're relatively close to where we're measuring. And what happens as the splines engage and disengage, it causes a ripple in the surface strain on the shaft. So we use those mechanical features to actually filter out the ripple in the surface strain on the surface of the shaft, which gives us a much cleaner strain that is better from a measurement point of view. It's quite a small sensor location, and it's a relatively small shaft, and it's measuring about 2,000 Newton meters. It's in a hot transmission, so we're seeing 150 degrees. We have a coupler which bolts onto the front of the gearbox, and then the electronics. We actually have an example of this on our stand. And really the key thing on here is our ASIC. So Transense, several years ago, developed an ASIC in order to drive the SAW sensor system. So the ASIC has an RF front end where we're generating that RF signal, and that is a controllable signal generator effectively. And what we're doing is we're telling it to send a signal to address one of the sensors. So at a particular frequency, we transmit a signal, then we switch into listening mode. We listen for the reflective signal coming back to the ASIC, and then we continue through all of the other sensors in the sensor system. So in this case, torque measuring system, we'd have 5 individual sensors that we're addressing, and we're going out to address and then listen and then address and then listen. And that's what gives us our measurement signal. In a lot of cases, the customers would just take an ASIC from us, but we have a complete reader. So this is a microcontroller where we're taking in the raw values, and then we're producing calibrated, temperature-compensated output from that by mixing the values together and applying a calibration algorithm. So it's pretty straightforward in terms of the processing that's happening in there. But as a complete system, that gives you something that can operate reliably in an application like a transmission in motorsport, obviously very high vibration, relatively high temperatures, and give you completely wireless transmission. So some of the examples of the SAW system in use. So one of the advantages that we have, or the opportunities that we have, is we're not dependent on the material that we're measuring. So some technologies are very sensitive to the material that they're measuring. And in applications, like particularly in robotics, people are very focused on the weight in the joint, so they want to use non-ferrous materials, things like titanium or aluminium. And this is an example of a flange coupler from a robotic joint, which is, we've integrated the torque measurement into that joint, so it can be a fully integrated torque sensor. And that actually allows the manufacturer of the robot to eliminate the separate sensor that they had previously, so it reduces the stack height of their joint and gives them a direct measurement. We have some other examples which are more conventional shaft applications, but just to give you an idea of how we implement the technology. Okay. So one thing that's always a very hot topic and is discussed a lot is accuracy. So what accuracy level can you achieve with the technology? So this is some information that we've never shared before, but it's around calibration uncertainty. So my engineering team gets very excited when we start to talk about accuracy levels and what do we actually mean by accuracy. And they much prefer to use this term uncertainty. Not really sure that I understand the difference, even though I am an engineer, but they get very deep into this. We have some examples here showing measurements at different temperatures. So basically the torque that we're applying, and then what the uncertainty level that we're getting out of that based on the measurements that we're seeing, so i.e. the accuracy level. So you can see that we're consistently achieving better than 0.5% here through the various different temperature ranges that we're doing the applied torque at. So the maximum error that we're getting is 0.46% at 100 degrees. So that's a pretty high temperature, you know, and actually a very good level of accuracy to be achieved in this. This is proven out then through statistical sampling and, well, 100% testing with statistical data gathering from larger quantity of sensors. So very, very low deviation coming from a large batch of sensors once they've been produced. So the thing with the SAW technology, fundamentally, the sensing elements themselves are made in a lithography process, so they're incredibly repeatable and very, very accurate in how they're made. So there's very little variation in the sensing elements. The sensing elements are placed using a very repeatable production system to put them onto the component that they're measuring, and the actual measuring technique eliminates a lot of the error that you would see with other measurement systems. So SAW gives you a very accurate way of making a torque measurement in something that can be built into a production system. What we also find is that because what does accuracy mean is quite a complicated topic in itself. So we've done some benchmarking of our technology against industry-leading sensors, so from some large manufacturers where they sell commercial off-the-shelf torque sensor systems. And normally they have this different accuracy classes, and we picked the best, the 0.1 accuracy class system. So you would think that our sensor, which is producing 0.5% accuracy, wouldn't be as good as a market-leading 0.1% accuracy class system. But what we found when we were testing them actually is because of the build-up of the various different error factors on that 0.1 class system, that in practice, when we were back-to-back testing them either on a standardized calibration rig or even better on a dynamic situation, so actually on a rotating machine when we were running that and testing it, that we see a much better performance from the SAW system. So even though the headline figure is 5 times the quoted figure from the off-the-shelf system, we're actually getting 5 times better accuracy, so in the other direction from the SAW system, a much faster dynamic response, so a 10 millisecond faster measurement coming out of the system compared to a conventional sensor, and 10 times the resolution. 10 times the resolution can actually cause you some problems because you end up with something that looks incredibly noisy. So you often end up having to filter that down. So it's a big topic in itself, and if anyone wants to discuss that, we pick it up on the stand. But the accuracy of our systems has been proven out, and this work actually was done by an independent third-party test laboratory for us. So it's been proven out to be very good compared to more conventional measurement systems. So one of the reasons we came to the event today was to launch some new sensors, but particularly because of really what is the main downside of the SAW system. So I'd mentioned it before in brief, but the key consideration that we are making is that when we look at a new design, we have to mechanically change the design to suit the sensing element. So we always say when we're talking to a new customer that there's a bigger upfront investment in time and effort in order to develop a SAW system, whereas if you were going to use strain gauges, that's a good technology to use if you want to make something quick and fast to get some basic test information out of, because you can pick different strain gauges and you can basically fit them to any component. Whereas we're looking at a very specific strain range, so we're trying to optimize the shaft design to go between plus or minus 400 microstrain. That always requires us to do some work to create an installation location and then the RF couplers. So what we found is in the test and measurement market, that's a significant blocker in terms of getting any new business. The customer would come to us with a problem and they'd say, we want to use your components on our test rigs. And we say, yes, that's great. We could look at that, but there's going to be an upfront cost because we have to design the system to suit the shaft, et cetera, et cetera. So what we've done is produced a number of standard shaft designs where basically the thing that gets customized is the splines on the end, but the bit in the middle is a standard mechanical part. And we've set these to some different torque levels so they could be more easily used by customers, either for testing the technology, which is something people might want to do if they're going to integrate it into a system. So most of the times customers looking to integrate it into their machine for production, not just use it in the test lab. So it might be a validation piece for the technology, or it could be a piece for the test lab. So this particular example on the right there is actually a motor manufacturer They had a 30,000 RPM electric motor for the automotive market, and they were doing a very dynamic driving cycle on it. And they were using an industry standard torque sensor from a large manufacturer, and they're having very, very big problems with torsional vibration in that torque sensor. So we looked at their system, and we worked out that we could replace the sensor and coupling system that they had on their dyno rig with a short shaft with a SAW torque sensor assembly on it. We did that work for them. They subsequently upgraded all of their dyno test rigs, so there are about 10 or 15 dyno test rigs in their facility, so quite a large motor testing facility. And it's enabled them to do these high-speed, high-dynamic test cycles without seeing torsional vibration coming through and corrupting their data. So it's been a really good example. And now we can offer the same concept to other people. And then a more conventional flange sensor system, which we have an example of on our stand. So we've various arrangements of this. It's got bearings in it, so it's got the limitations of a bearing torque sensor assembly, but that is what some people need for some applications. So moving quickly on. So in the test and measurement market, we can see that there's some really clear benefits from the SAW technology. We're very, very sensitive, so we can measure force on stiff components, very low hysteresis. That gives you a very low latency, high dynamic response in the system. The SAW sensors are very small. Maybe hard to get that idea from these slides, but we can show you some examples on our stand. So they're incredibly small. They can be fitted into a very compact space. So typically we see people putting these where they can't fit a more conventional sensor. They've got exceptional reliability over time, so the performance really doesn't degrade over time, virtually zero creep in the system. So that then gives you a very robust sensor that can be integrated into a production system with a very long life expectancy. We can integrate them directly into electrical machines, so for torque measurement, but also for temperature measurement. So we have customers who are using this to measure magnet temperature in electric motors for automotive traction drives, in order to allow them to reduce the rare earth material content. The ability to measure strains and therefore forces and torques and temperature simultaneously means you can have fully temperature corrected systems without having to install extra sensors and extra electronics. Completely passive, so you don't need any extra power on the shaft. It's a big advantage, and very, very repeatable. So not so relevant if you're making stuff for a test lab, but if you want to put a sensor into production and make 1 million units a year, that's quite difficult normally for a torque sensor. It's much more achievable with a SAW system. So I think in conclusion, and to give some time for questions, we've got a huge sensing market. We can see a great turnout to this exhibition. The market's growing. We see lots of opportunities in things like robotics and some huge challenges. Really low latency, highly dynamic sensors are in big demand. So it's all fine and well having a sensor that performs very well statically, but almost no application in the real world is taking a measurement statically. So being able to measure reliably and repeatably in a dynamic manner, very, very important. Conventional sensors do have their limitations, varying different technologies, typically in terms of reducing stiffness and then higher overall life cycle costs, which we can help address. And the new technology, such as SAW, and I would still call it a new technology because very few people have actually heard of it before, which is why we're here today. It provides some new opportunities in terms of how you can design a system and how you can integrate the sensor into that system. So that's all from me, and happy to take questions. Yep. How do we do it?
Just a question. What about the cost of the system?
The cost?
Yeah.
Okay, great. So the fundamental components, the sensing elements themselves are relatively low cost because we make them at wafer, so it's a wafer process. would say to people the production process for the sensing elements is very similar to a MEMS sensor. So it's fairly straightforward metallization and lithography on wafers, diced, and then produced. So the sensor cost is pretty low. We have an ASIC, and the ASIC is an ASIC. There's not actually that complex in terms of the structure of the ASIC. We're launching a new ASIC at the moment for 8-inch silicon, which also can be pretty low. So depending on the application, very much affects the cost of the system. But we see this as being competitive even in really low-cost applications like e-bikes. Obviously, the requirements are less in those applications, but we can be competitive in that market. At the same time, in the aerospace market, we're directly making torque sensor systems for helicopter engines and turboprop engines. Obviously, that market, the sensors are much higher cost, but we are very cost competitive in that market because fundamentally the systems are easier to put together. Okay. Any more questions? Okay. Yeah.
About the turning of the part, can you see the revolving speed and so on? You can see that, right, with a signal.
So fundamentally, obviously the parts are designed to be installed on rotating components. The design of the couplers is designed such that it takes out the majority of any effect on the signal from the rotation of the part. If you were looking purely at the amplitude of the signal, so we don't actually use the amplitude of the signal, but if you were looking at that, you can see it vary slightly as the component, basically elements of the RF coupler pass each other. So you can pick up these very slight peaks in the amplitude of the signal that indicates the rotation of the part. We don't look at that as part of the measurement system. We have done some work, though, in saying, well, actually, could we use that as a very crude speed indication for the part? So we worked out a way where we can put some extra features into our coupler to sort of deliberately cause these amplitude peaks. And we can count them and get a fairly basic speed feedback from the system. What we found, though, and actually we have 2 running programs for this now, where people want a much more accurate speed or position feedback from the part, we can integrate an inductive position sensor into our RF coupler. So we then have a hybrid sensor system where the RF coupler can actually serve twofold as our RF coupler for the torque sensor or the temperature sensor, but also as a inductive position sensor, and that the sort of off-the-shelf position sensor technology can pair up with our sensor really nicely.